Another important data structure concept is list. A linked list is a data structure in which the objects are arranged in a linear order, unlike an array, though, in which the linear order is determined by the array indices. The order in a linked list is determined by a pointer in each object. Linked lists provide a simple, flexible representation for dynamic sets supporting all the operations search, L of L, K, insert, L, X, delete, L, X, successor, predecessor, minimum, maximum. W linked list. As shown it here, each element of a doubly linked list L is an object with a key field and two other pointer fields, next and prev. The object may also contain other satellite data. Given an element X in the list, next of X points to its successor in the linked list, and prev of X points to its predecessor. If prev of X equals to nil, the element X has no predecessor and is therefore the first element or head of the list. If next of X equals to nil, the element X has no successor and is therefore the last element or tail of the list. An attribute head of L points to the first element of the list. If head of L is nil, then list is empty. Here, if we look into an example over here, L represents a dynamic set 7, 11, 4, 19. Each element is in the list is an object with fields for the key and pointers to the next and previous objects. The next field of the tail and previous field of the head are nil, indicated by diagonal slash. The attribute head of L points to the head. Following the execution of list insert LX where key of X equals to 25, the linked list has a new object with key 25 as the new head. This new object points to the old head with key 7. Then result of the subsequent call list delete LX where X points to the object with key 19. A list may have one of several forms. It may be either singly linked list or doubly linked list. It may be sorted or not, and it may be circular or not. If a list is singly linked, we emit the previous pointer in each element. If a list is sorted, the linear order of the list corresponds to the linear order of keys sorted in elements of the list. The minimum element in the head of the list and the maximum element is the tail. If the list is unsorted, the elements can appear in any order. In a circular list, the previous pointer of the head of the list points to the tail, and the next pointer of the tail of the list points to the head. The list may thus be viewed as a ring of elements. In the remainder of this section, we assume that the lists with which we are working are unsorted and doubly linked. Searching a linked list. Here we have a procedure to search a list. List search L, K finds the first element with key k in list L by a simple linear search, returning a pointer to this element. If no objects with key k appears in the list, then nil is returned. To search a list of n objects, the list search procedure takes theta of n time in the worst case, since it may have to search the entire list. Deleting from a linked list. The procedure list delete removes an extreme X from a linked list L. It must be given a pointer to X and it then simplifies X out of the list by updating pointers. If we wish to delete an element with a given key, we must first call list search to retrieve a pointer to the element. Here is the procedure for algorithm for list delete. List delete runs in order of 1 time, but if we wish to delete an element with a given key, order of n time is required in the worst case because we must first call list search. Sentinel. The code for list delete would be simpler if we could ignore the boundary conditions at the head and tail of the list. List delete lx next of previous of x points next of x previous of next of x points previous of x. A sentinel is a dummy object that allows us to simplify boundary conditions. For example, suppose that we provide with list L an object nil of L that represents nil but has all the fields of the other list elements. Wherever we have a reference to nil in list code, we replace it by a reference to the sentinel nil of L. As shown it here, this turns a regular doubly linked list into circular. Doubly linked list with a sentinel in which the sentinel nil of L is placed between the head and tail. The field next of nil of L points to the head of the list and previous nil of L points to the tail. Similarly, both the next field of the tail and the previous field of the head point to nil of L. Since next nil of L points to the head, we can eliminate the attribute head of L altogether, replacing references to it by references to next nil of L. An empty list consists of just the sentinel, since both next nil of L and previous nil of L can be sent to nil of L. The sentinel nil of L appears between the head and tail. The attribute head of L is no longer needed. We can access the head of the list by next nil of L, as shown it here. The code for list search remains the same, but with the references to nil and head of L changed as specified it here. We use the two-line procedure list delete to delete an element from the list. We use the procedure insert to insert an element in the list. So here it shows the effects of list insert and list delete on a sample list. Sentinels rarely reduce the time bounds of data structure operations, but they can reduce constant factors. The gain from using sentinels within loops is usually a matter of clarity of code rather than speed. The linked list code, for example, is simplified by the use of sentinels, but we save only order of 1 time in the list insert and list delete procedures. In other situations, however, the use of sentinels helps to tighten the code in a loop, thus reducing the coefficient of, say, n or n2 in the running time. Sentinels should not be used indiscriminately. If there are many small lists, the extra storage used by their sentinels can represent significant wasted memory. In